is always automatic. Okay. Okay. Nice. Have homework 8 that was due Tuesday apparently, so we can make it due today also. It's fine. Homework 8 was due today. Due today, yeah, okay. Homework 8 due today. No, that's it. Set it. Mine is yeah, let's make it 6. Thursday. I think it writes April 4 up there on the homework. So I think it's 6, it should be. Okay, and the midterm 2. There's also like thank you to all of you guys for helping out with the math field day. And I thought I should take you guys for dinner for that. So another assignment is your come for dinner, but it's not an assignment. Okay. So the dinner, this is purely optional, it's free. That means I will cover. It's optional. You don't have to attend. Not for assessment. I want, if you do not show up, it's not like a homework. So it's tomorrow, Friday, 7:30 p.m. And you can bring friends. Don't bring too many, and don't bankrupt me. Bringing
I wasn't helping. Can I join?
Huh?
Too? I wasn't helping. Can I join too?
Yeah, all of us. Yeah, no, you helped, right?
For the
Yeah, math field day. You gave support. Mental support.
Telekinesis.
Yeah,
Transfer guard.
yeah, all that matter. You did not complain that the class was cancelled. You allowed the class to be cancelled. That's a support. No. So that's, I think, I mean, probably you guys have something out there going on. So that's okay. So, yeah, again, simple dinner, I don't promise. Yeah, we have to select a place. Can you guys select before tomorrow or before in the end of evening today? Do you guys have a good place in mind?
Wait, for
Dinner.
we all meeting.
Is that possible for you guys all to meet?
Restaurant or?
Yeah, probably people need a ride, right? Yeah, how do we do this? Yeah, Ryan, tell me.
I can get it right.
I can do.
So, okay, 2 of you and you're
Actually,
6. Are you, will you be able to join? Because you might be going
No,
home.
I think I'll like.
Yeah, so you will skip, that's okay, no assessment, so you can skip your homework. So, but then you cannot give right either. Yeah, so. Yeah, so ask me if you do not have a right. And otherwise find a right. Okay.
Okay.
So we meet at the place. Where is the place? Do you guys know anything?
think the
I
nearest
haven't
place
tried
is
playing this.
Quatros
Quatros,
is the nearest place.
nearest place, that's a good place. Quatros. Anyone else want to suggest something?
What is this called? Primos,
Primus,
Primos.
I don't know actually.
There's a
Where is that?
The pizza place.
Is that place?
That's. Right off of East Park Street. in Carbondale. It's- If you,
Seen this
it's on, it's on the east side of. Well, just after the east side of campus. So,
Think I see
if you go past the,
crossing,
go across the railroad tracks, right?
like a
Take
bus-
campus, and then
yeah,
make a left at the light. And then. A right, very next right. And then it's right there on your right.
how about this, I suggest we try something more than a pizza place. Like pizza you get more often, right, so since I'm covering it, so. Use the opportunity to go here.
It looks good.
Better than a pizza, I mean, pizza is okay, I love pizza, but I'm just saying it's easier to have for you guys. Right? We should ask Matt, maybe he from, yeah, what did you say?
Buffalo wings.
Buffalo wings, that's good, yeah, I have never been to the Buffalo wings here, I think, yeah, but that sounds good, yeah.
That's
That's good.
We were saying there's a new homework assigned, you had to attend a dinner, but it's not for
Is it
assessment,
required?
you can skip, huh?
Okay.
Yeah, you don't get points, but then you can skip also, so if you don't, I don't give point, you can have to skip. Which is okay, so then we were saying, what is a good place, the suggestion was. First was the pizza place, which I shot down. So then second is Buffalo wings, and you have your prop Carbondale, you should know, good places.
Some places I like here, Thai taste is pretty good, if you
Okay.
like Asian type food, bandanas is good if you like barbecue,
Which one is it?
bandanas,
Bandanas, yeah,
if
yeah,
you like
okay,
barbecue,
yeah, yeah.
or just meat in general, like.
Mhm.
Um, Chinese probably would be Hunan,
For now,
yes,
is anywhere fast,
Quattro's for pizza.
who else is fasting other than Abdullah? Is anyone fasting? Okay,
Me too.
me too,
Oh,
but you're not coming, so
Okay.
so 7:30, that's why we chose the time to be 7:30. Hopefully, the sun is down by then.
Yes, sunset,
Yeah.
I think it's
7:18 or.
17, might be fun. Yeah,
Okay, okay, so we'll be fine with that, okay. So. Buffalo wings is one option, so can you guys talk among yourself and let me know a suitable place? Okay, so you have a group among yourself, right? We'll discuss.
Yeah.
And decide by, otherwise I'll not know where to come. So do let me know. So-
Show up a random.
Okay, so let me know. Don't make it too late. Let's say sometime before tomorrow afternoon, so that I know where to go. Okay. And oh yeah, I was also wanting to say, I did, this is pretty much the class activity, but I invited Rana, yesterday I ran into her and she was talking about dinner because she's graduating, so I invited her also, if that is okay.
Yeah,
So
that's
it's, okay. So we'll have one more student other than that class. Okay, so, okay, so is that okay? So you guys
Yeah.
come, okay, good, okay. So that's the hard stuff, let's do some easy stuff. Right, so deciding on the place. Okay, last time we introduced Maxwell's, or we started from Maxwell's equation and we said that we can introduce a potential, electric potential. And magnetic vector potential, electric scalar potential, let's say. Write it down. Phi are both position and time. Electric scalar potential. And vector A. Again, position and time dependent. The magnetic vector potential. Once we know this, we know the electric and magnetic field. Electric, magnetic field. It's nicer, simpler. Not necessarily simple. Is the curl of the vector potential and the electric field is the gradient of the scalar potential time derivative of the vector potential. So clearly, it tells us that if we know the scalar potential and vector potential, we can find the associated fields, which is electric and magnetic field. Because there are derivatives associated with this is not unique. You can have more than one electric and scalar and vector potential that contributes to the same electric and magnetic field. That's called the gauge freedom. And we have been using the Lorentz gauge, or we said we would use the Lorentz gauge. So we use Lorentz gauge. Which is d mu, a mu is equal to 0, which is also written as where I this d by dt of phi plus dA by dt. Great divergence of A. Is there a C floating around? I'm not equal to 0. Is there a C floating around? So that's 1 by C. That's the A mu is on. Is there a C square? I mean, you guys,
Yes, 1 over C.
1 over C.
C squared.
1 over C square. Okay. So that's the Lorentz gauge, and we said that if this satisfies the differential equation, the wave equation. So charge density. And it's pretty much the same equation, except the source is different. Mu naught times J. Whenever we have an equation in homogeneous differential equation, on the right side, we replace it by a point source, and that's called the Green's function. And here in this context, we call it the retarded Green's function. We'll come to the name later on. That's retarded Green's function. The idea is that if I can solve for the differential of the Green's function, I know the solution for everything. It's like the electric potential in the case of electrostatics. So the equation of interest is the following. Square, and this is the Green's function. It's R minus R prime and T minus T prime. On the right hand side, I simply put a delta function R and R prime, but this time I also put a time. So it's equivalent to putting in a charge there. So if I were to think of this charge density, I'm keeping a charge at one point. So remember, this is the same as delta of x minus x prime, delta of y minus y prime, delta of z minus z prime, and t minus t prime. So I pick my x coordinate to be x prime, y coordinate to be y prime, z coordinate to be z prime, and the time coordinate, I'm fixing the time so that exists a source in a sense. Let's say think of a charge, and the contribution this is getting is only at t equal to t prime. So imagine you could switch on and off a charge, the presence of a charge at t equal to t prime, you switch on the charge exists, and you switch it off. And you're asking what is the electric field associated with that everywhere, electric or magnetic field associated with that. So that's the physical picture you want, but if we know the solution, the idea is that we can do a lot from here. So let's get the solution once and for all for this case. It is, we don't lose any significant generality here if I choose r prime to be 0. So let me choose r prime to be 0. I choose my origin basically at the position r prime, and let me choose the origin of time to be t prime is equal to 0. Later, when I reach the solutions, I just have to say that replace all my r with r minus r prime. Right? And wherever I have a t in my solution, replace it with t minus t prime, and I'll get back my general solution. So I'm really not losing any information by choosing making that assumption. Okay, so that's square. So that's one simple. I do, maybe one should point out that in general, this is r comma r prime and t minus t prime. What I've used is that if you just have a single source and a single observer, whatever it depends on is only the distance between them. Like you cannot have, so if you have a source here, let's say think of a positive charge here, and you're observing, observer is down here, right? Whether I'm having my frame here or here, right? It doesn't matter, right? It's going to be the distance between them. So I'm making some assumptions there about the system, how it is working. It is called, I'm using the homogeneity or the linearity, locality in a sense. So those assumptions are being made, and I've already said that r minus r prime. So, but that's mostly okay. It's basically saying that when I translate my space, nothing is happening.
The argument for the second equation for delta function. It r
This one, t minus t,
for the second one.
this one, yeah.
No, below
Oh,
that.
here.
Yeah.
Oh,
The
so,
argument for is-
I'm just writing that, so I was in between, I got distracted. Right, so, okay, so
the
this,
same as the Green's function.
this is the same as the Green's function, except I've chosen my origin, coordinate system origin to be r prime equal to 0, t prime equal to 0. So I choose this, and later in the solution, if I do this, I get back my general. So I really don't lose anything. If at all one has to argue, why did you argue that it is r minus r prime and t minus t prime? There I have made some symmetry arguments that if I have an observer and a source, it can depend only on the distance between them. It cannot depend on, there's nothing else, there is no reference. Like imagine you are in space and there are no stars you can see. There is one, that's one is you and that is another friend. And you have to tell someone else that is your friend, that is no reference. Typically you say, oh, that is a McDonald's, that is a gas station, it is to the east of that. But if you don't have that reference, that line connecting you two is the only reference, that's all. So you, things cannot depend on anything else, right? There is no vector to begin with. There is no reference line, infinity is too far. Right, so it's a, that's called symmetry argument. So we have used that to write that down. But with that, so we are here. And let's now, so we want to now solve for this Green's function. And remember again, if this term was not there, right, that's the static situation, right? In the static situation, so let's also say what is happening in the static situation. So static case is minus del square. And let me call G naught. Yeah, let me come back. Yeah, let's say R, there is no T now, that's the Q R. That's the static Green's function, which is basically the electric potential due to a point charge. So there's a point charge with unit magnitude if you want. What's the solution to that? What's the solution to the Green's function for the static scenario?
It's 1/4 pi over 1/r.
1/r, very good. So it is 1/4 pi r, that's it. Electric potential due to a point charge, it is usually Q/4 pi epsilon naught. Epsilon naught has been like Q/epsilon naught, we have set to 1. Right, so that's all that is, and that's the solution. If you had chosen this, if you want to upgrade your solution to your origin being somewhere else, then you would say this is 4 pi r minus r prime, magnitude of that. Right. So that's for the static case, right? And we should have our answer in that, like whenever we do something which leads us to the static case, we should have that solution inbuilt in us, and we will use that as a reference. We will say that at some situation, this should reproduce that. Okay, so that's good. And let's go back to our actual Green's function and let's Fourier transform. Like we are going to Fourier transform, work in frequency space, and then come back. Right? So let's say G of RP. Whenever we Fourier transform, so suppose you have a Why is that not working? Okay, that's okay.
Yeah, so sit here.
Huh?
Yeah, so sit
You have
here.
to sit here, I see. Oh, because this is.
The sensor.
Yeah. Sensor is, okay, fine. The next time you want to keep this a bit. Okay. Think of this as a function of time, any function of time, any signal in time, any function of time can be expanded in times of sine and cosines or exponentials, which are basically sine and oscillatory exponentials, which are sine and cosine. So that's a Fourier transform, and everyone is familiar with Fourier transformation here? A little bit, but yes, basically expanding, writing music in terms of tones, right? So that's all the idea we want, or as a mathematical statement, you're saying addition is now being replaced with integration. So this is the addition over all frequencies, So think of every note, is that what you would say? Every tone, every note in music. So for every frequency, the musical note will be I omega t, right? This is sine and cosines, right? Sine omega t. And you can expand that, and the amplitude associated with each of those musical tones is going to be called G of R omega now, right? This is, in principle, this should be another function that's still there, but I'll stop writing. So it will be understood that whenever this is frequency dependent, it's another function from that, but I use the same.
Is that included in the integral or?
Yes, this is included in the integral because it's omega dependent. So it's like saying you have sine of let's say 20 hertz, right, times t plus sine of 40 hertz times t plus, think of every frequency possible. And the claim is that the idea is that give me any kind of music, any music that you can think of, I can choose how much amplitude I want to put in. So let's say this is 1, this is 0.5, This is, I choose my amplitude 0.3 and so on. And I get every possible music you can generate out of that. And this choice of amplitudes is what this is. This function is the choice of the amplitude for every frequency. That decides your music. So this is the music. This is the choice of the amplitudes you associate with every, I think it's called a tone, every note that you can click on. And usually in an instrument, there is a finite number of tones, so you can generate only a certain kinds of music. But if you give me all the frequencies, then you can generate any music you want. Okay, that's the idea. And the main point is that if I know this, I can do the inverse also. If I know, and as I said, I will stop writing the tilde. Because omega will give me the kind of information that it's a different function. I can get the other one too. So this one is integrate over time now, minus infinity to plus infinity e raised to actually I change my notation. This will be minus, right? So this will be plus I omega. I changed the notation. I did made it minus.
The integral is from minus infinity to infinity or 0 to infinity.
Minus infinity to infinity. Frequency will be both negative and positive. It turns out that it will be the identical. When you think of it as music, then it is the same. But as a mathematical function, my sine of minus omega t is also possible, but they are not independent. That's our main thing. But in this case, it is minus infinity to plus infinity. If it is identical, you just make it 2 times. Is that clear?
Because it's time, so time should be from
No.
0 to.
Oh, you mean to say causality? Is that what you're bringing? I don't assume causality at this point. At this point, I'm not assuming causality. So the good point, what Arjun is saying is that we are saying there is a source and there is an observer. It is expected that the source, whatever it does, should happen before what you observe, right? That's what the physics comes in. But at this stage, I don't assume that. But hopefully, probably, we should have that condition, right? Because we don't expect that light ray first comes and hits me and then the source bulb lights up. That's not expected. So somewhere causality should come in and we'll see that, right? So this will have 2 solutions. Just to give you the answer, there'll be 2 solutions. One will be not causal, one will be causal, and we will choose causal solution. Right, so that's what will be the case. But here, both solutions we are keeping the general solution. So this will be equal to R comma T. Okay. So the idea is if I can solve for this, do the integration, I'll get this. So instead of working in time domain, I'll work in frequency domain and then do this integration to get the time domain. That's the idea. But what is the equation for this omega? I have to do this differentiation, right? So let's say time derivative of g of RT is equal to time derivative of that whole integral. G of R omega. The advantage of Fourier transform is that when I take derivatives, it becomes very easy in the sense the only place where there is a time is the exponential. Only place, right? Because I converted to frequency, but I have to be inside of the integral. That's the only point I have to make. So take the derivative in, it acts on this, and it is minus infinity to plus infinity omega over 2 pi exponential. And I bring down a minus I omega, right? Times G of R comma omega. The square brackets have no special meaning in there. It's just to clarify that the time derivative basically no special meaning to those square brackets. It just means that inside, as far as you stay inside the integral, wherever you see a time derivative, you replace it with minus I omega. That's all you're doing is Fourier transform as far as the user, if you think of it as a algebraic expression, that is all that is happening. If I say, make another time derivative act on it. So now I'm doing another time derivative. That will act on here, so that's the second derivative, that will act on here, it will bring down another minus I omega, so that's just square of that. So only thing time derivatives just in a Fourier transform is that change this into frequency, that's actually that one. Right, it becomes algebraic, all the calculus becomes algebraic, and that's the advantage of Fourier transform, all derivatives becomes just algebraic expression, yes.
And when did that become minus W squared, because I squared.
That's correct. Minus square is 1 and I square is -1, so it is minus omega square. And that's frequency, so it's omega, not W.
Oh, yeah.
Yeah, but when I write it, I write my omega and W the same, so it's my fault, but at least when you do it typographically, there's a small subtle difference between the two. Okay, so if that is the case, do the same thing here, right? But I'll take care of this time derivative, but there is a time derivative on the right side also. What is then we ask what is the Fourier transform of the delta function in time? So that was a function we are interested in solving. What's the Fourier transform of a delta function? Delta function is only at time t equal to 0 something exists. And what is the Fourier transform of a delta function? So maybe think of this, right? So what should this be so that that's a delta function? Maybe think of it like that.
Before omega,
Tell that again.
delta omega.
Delta omega. Delta omega. Or what should I write here so that I get this? Huh?
It's a delta function.
Step function, derivative of a step function is a delta function. But think of an integral, think of a function that I write here will give me a delta function. Constant, very good. In fact, choose it to be 1. Very good. Right? Choose it to be 1. Right? Very good. Right. So just choose this to be 1. So what's the Fourier transform of a delta function? That's 1. Right? In general, to have a mental picture of it, if you have a function like this, a stretch, this is in time. Right? How much you spread the function in time, it doesn't have to be a plateau. How much you spread in time and how much you spread in frequency, they are related. If you spread more, so if you compress this, frequency will get larger. So let's say this is time, this is frequency, product of this is a constant. And that is, where does that show up? That's a quantum mechanical thing. Quantum mechanics uses this a lot. Heisenberg uncertainty principle of frequency, spread in frequency, spread in time is related. There is angle, momentum and position that are related. So the idea is that if you have a signal which is spread out a lot in time, if you think of the frequency, how many keys you have to press on piano to get that, that will be very few. If your signal is spread out a lot in time, then the number of keys you have to press is very few. If you have to press a lot of keys, then your signal is probably just a blip. It just comes and goes. So that's simple. That's a geometric picture, but for our purposes, this is just that the Fourier transform. What is the algebraic? What is the Fourier transform of 1? That's the delta function. Good. Okay. So if we do this, put this in our equation here, they have a differential equation shows up there. So that's del square. I have 1 over c square in there. Mass pointed out that that's nothing but minus. So this becomes plus omega square over c square times g of r omega. And on the right side, delta function is the same integral. Everything is showing up inside an integral. But if it is a complete set of functions, each one is that equality holds for each frequency. And this becomes delta function of r. This whole thing is inside an integral actually. So it's good to appreciate that. This whole thing is inside an integral. But then why does, like, just because the sum of something is equal to 0 doesn't mean that each component is 0. That's because this is a complete set of function. This is like a vector. When you write a vector is 0, each component of that is 0. So there is more points going in there than I'm emphasizing. But if we use the Fourier transform, we basically get a differential equation in this form. Is that clear? An equations at this stage. Mostly conceptually I'm going here, but very soon we will go into the actual differential
Where
equation.
did we get that last one?
This one, I substituted this for, okay, I substituted this in this equation. So second derivative of time gives me omega square, but then I have an integral, so that's an integral outside. The omega over 2 pi exponential of minus I omega t. With me? Okay, and the delta function on the time is also an integral. So this whole thing is true. Right? But if you have sum of let's say x plus y, so sum of xi, I going from 1 to infinity to be equal to 0, does that imply xi is equal to 0? No, right? It doesn't. But it seems like that's what I'm doing here. There is a sum over frequency, but then I'm dropping the sum. But that's not what it is. If I were to write the same thing in the form xi times ei, a vector, right? I is equal to 1 to infinity, then this is equal to 0. The components of a vector, because they are complete set of functions, they are orthogonal to each other, that's equal to 0. Is that clear? So this is a complete set of functions. The Fourier functions are complete. I need that. Fourier functions are complete. So in that sense, I have used a lot of, so even though I'm using Fourier transform, as I said, at a very user level, I'm basically using all those ideas. Is that clear? Okay, any questions on that? Yeah.
We are getting Fourier transform like in the other equation. We are there.
I start from here
So we are getting Fourier transform both sides, right?
on both sides, exactly. So
Okay.
get rid of the time
Yeah, then we will have both like integral parts on both sides.
on both sides.
Then apart from that part, we can equate the other part. Right?
Correct. Only if it is a complete set. Only if when a vector A is equal to vector B, that means the components are also the same. Only if it's a vector, but if it's a scalar equation, that's not true. Right? So they usually sometimes, I mean, naively, you can think, oh, why is the sum equal to 0? That means that each frequency is equal to 0. So that's because these satisfy the properties of a unit vector. This forms a complete set of orthogonal functions. So that is a concept that has gone in. If that's true, then we immediately get this to be true. Okay, the thing. So the strategy again, this was our main equation, or let's say here, this was the main equation. We made a simple choice of origin. We got this. We Fourier transform and we are here. That's nice because this is very similar to the static case. Like this seems to be almost the same as static case, except that is of course frequency. That's like as a second term, which tells me what should I do here to get the static case. What should I do to get the static case? From here to here, what's the connection? Setting the frequency to be 0, right? So omega equal to 0 implies static case. Why?
It's not time. Or not time.
Yeah, why is frequency setting to 0 means no time?
Because frequency to change time.
Huh? Frequency is change in time. That's actually correct, 48 times, that's a time, derivative, yeah, that's a good answer, actually. Yeah, it is a change, in time, very good. Or you can say that, the time period is so large. So I said, as you increase your time, the frequency becomes small. That's another way of geometrically seeing it, but I think I like your answer that this is a time derivative. And if omega is equal to 0, that means the time is not changing the time. So it is static, means frequency is equal to 0. And we know then, so we have a condition. So this will be called a boundary condition or an initial condition. So we need a boundary condition now. So we have learned that whatever we are looking for, we would like to have, whatever is the solution, it should satisfy G of R 0, the frequency is equal to 0 should be 1/4 pi r. That's a boundary condition or initial condition, whatever you call that. It's boundaries are typically associated with position. This is in frequency, so in that sense, this is not really a boundary or an initial condition, but in mathematical sense, it is the same scenario. Okay, good. So that's what we have now. One more symmetry argument. So we have a source here right at the origin. So this is now at the origin. And something that's your observation point. Observation point. If you have some physics happening in here, it cannot depend on where your system, the orientation of your origin, right? It should depend only on the distance r. Right? It cannot depend on the orientation, whether you choose your axis to be like this or like this. It cannot depend on that. Like universe has only 2 points, it can depend only on the distance between them. So that is, and that's what we see in the scalar case also. So that should be true here also. So let's say spherical symmetry imposes the condition that R, actually the dependence in R is basically the magnitude of R. That means minus L square plus omega square over C. This is basically only an R dependent quantity. That is no angle theta and phi. That's equal to, so no, so R is R theta phi. There is no theta dependence, no phi dependence. But that should come up on the right side in a sense also. So what is the delta function on the right side? This is delta of R, delta of theta, and delta of phi. What am I missing? What's the delta function in spherical coordinates?
Or
There is 1/r squared.
1/, dimensionally, this is not correct, so I should have the scale, the length associated with each of those variables. So that's r squared sine theta has to show. Basically, we are going from this equation and trying to get rid of all the angular features. We are saying that we don't want any angular features in here. It should depend only on r. So that's my this more explicitly in spherical coordinates is this. Now what I do is I'll make this operation. What is a Laplacian in spherical polar coordinates? What's the Laplacian?
R, your,
Yeah, and
plus sine theta. Yeah,
very good.
theta
Plus,
plus 1/r squared.
oh, I think this I wrote wrong. This, no, this is okay. Yes, I'll square times square. Is square. Okay. That's a whole operator, but on the left hand side, this doesn't depend on angle theta and phi. So this and this is 0. Right, that doesn't operate on it at all. So this is still just processing our equation. We are not said solve, we have to eventually solve for the differential equation, right? This is, we are bringing it down, making it simpler and simpler. That's all. Plus omega square over c square times g of r, r magnitude omega is equal r delta theta delta phi r square sine theta, right? I still have angles on the right hand side, right? How can I get rid of it? If I want to work in the radial coordinate, how do I work with this? What's the algebraic trick you will use? I mean, like if you notice, I'm simplifying, right? There was first R and T, there were 6 variables and chose an origin that made it 4 variable. Time I went into frequency, now there is now time to worry about. So I'm left with 3 variables, use spherical symmetry. I'm interested in working with only R. But on the right hand side, I have this theta and phi, right? What's the algebraic trick I will use to avoid that angle theta and phi? Integrate it, right? Whenever there's a delta function, you want to get rid of it, you integrate it, right? And I'm integrating over angles, so things are, hopefully R is the important piece. So I do an integral on both sides. Left side, there is no angles at all. So if I integrate over the whole sphere, there will be 4 pi coming in. So on the left hand side, I have 1 over R, d by dr, r square, d by dr plus omega square. And this is 4 pi times g of r omega. And what do I get on the right side? Basically, what is the integral I'm doing? It's good if I specify that. So this is d theta, d phi, but then I'm doing it on a sphere, right? On the surface of a sphere. So this is r squared sine theta. 0 to pi, 0 to 2 pi. With me? Okay. And this is delta of r, delta of theta, delta of phi, and r squared sine theta. And these two cancel out exactly, that's needed. And then the integral is doable, theta and phi is somewhere in that, on that sphere. I can do that, and that's equal to 1. So that's delta of r. So eventually I have a one-dimensional differential equation. That's usually easy to do. The whole goal here was that we started with 6 variables in there, and eventually we are in a one-dimensional R-dependent quantity, which is hopefully easier to handle. Okay. Space, I think I can go here. Okay. Any questions at this stage? And remember, we still have this condition. This is 1 over r should come out, and that leads to the substitution. So I'm interested in g of r omega. I know that at omega equal to 0, it is 1 over r. So why not find a solution of that kind? That we begin by saying that this is 1 over r. Whatever is unknown, I'll capture it in r omega. So I've not done anything. I just presume, hopefully, that is 1 over r. If it is not there, then this 1 over r will go into that. So I don't lose anything by giving it a structure of that kind. Then what is my equation on the left hand side? So that's 1 over r squared, d by dr, r squared, d by dr of g is equal to 1 over r squared, d by dr, r squared. That is 2 of this it can hit on. Whence it can hit on dg, so that's 1 over 4 pi r times partial derivative of g with respect to r, or it can hit on the denominator, which just gives you g over 4 pi r squared. R squared can multiply in now, so that's 1 over r squared d by dr of let me pull out the 4 pi also. R squared r times partial derivative of g with r, and this is minus g. So that's one of the derivatives, but I have to do the second derivative also, operate the second one. So that's 1 over 4 pi r squared. When I hit the r, I get a 1. That's 1 times partial derivative of g with respect to r. When I hit the second term, so it's plus r times second derivative of g with respect to r minus of dg by dr. That's convenient because one of the terms cancels out. That cancels out, and what I have is this is simply equal to 4 pi r times second derivative of g with respect to this is second derivative, so that's r squared. That's a simple algebraic expression. Use that in here. Right, so now I have a structure there. Use that in here. My equation reduces then to minus of this is 4 pi r. So this is 4 pi r times second derivative of g with respect to r plus omega square over c square times 4 pi. Hold on, this has to act on this, right? Or how do I write this? Okay. So this is I've already done the g, but there was a 4 pi also there. So this is a g times the 4 pi. And that is minus omega square over c square times g, 4 pi g. So it is 4 pi times small g over 4 pi r. And that's equal to delta function. R. Right. Did I get everything? Oh. I guess that's R, that's R.
No, like in the numerator.
In the numerator, there's an R, and why do you say that? This is R squared actually.
Oh, okay.
So it's R squared. Right, so that's what 1 over R squared, that comes out 4 pi R. That's, I think that's all, probably all okay. Okay. Hopefully, yeah. Okay, so 4 pi cancels out apparently. And what I have is second derivative of g with respect to r square. Let me make this plus, right? Plus omega square. I can write that as, I just want to write this as minus second derivative of r square plus omega square over c square times g. And g is a function of r and omega. And that's equal to r times delta of r. Well, okay. So that's a differential equation in one variable, typically easy to solve. And remember, r is greater than 0. Or r is greater than or equal to 0. At r equal to 0, I need to satisfy that condition that it should on the boundary be 1 over r. So let me talk about situations where r is not equal to 0. And then I'll extrapolate it to r equal to 0. So r not equal to 0, we know very clearly what is the right hand side for r not equal to 0? 0. 0, because there's a delta function, right? Delta function survives only when r is equal to 0. So that's gone. So what I have is r squared minus plus omega squared over c squared, g is equal to 0. What's the solution to that equation? What's the solution to the final equation?
Sine, cosine.
Sine and cosine, it's a harmonic oscillator, right? Very good. So the final equation that I've written is nothing but second derivative of r square of a function is equal to minus omega square over c square times g, right? Think of a function whose second derivative is a function itself with an opposite sign. Second derivative of sine is that, second derivative of cosine is that, or second derivative of exponentials is that. So two solutions for this is r omega is equal to two solutions, so a times exponential of I omega over c times r. Right, the position. So dimensionally speaking, it's in the denominator plus b times exponential of minus I omega c over r. R is the magnitude, is the distance between the source and the observer. Is that clear? Right, any questions? Now we have solved, and now we have to go back. Like we simplified from 6 variables, we went down. Somewhere we had to solve the differential equation. We solved it in one go. Like we reached a place where there was a familiar differential equation, and now I know G, small g. Once I know small g, I know capital G. Once I know capital G in frequency, I have to substitute that in this, and I get back my time dependence, and then reconstruct, move my origin, and I get back my full solution. That's the goal. So we basically, as far as technicality goes, we have solved the equation. It's just that we have reconstructed at this point and do one more integration. So, and there is two unknowns, right? A and B, and we should also make sure that we get back our solution when omega is equal to 0, right? So let's go back and write that down here. So G of r omega is equal to, put that in here, right? So this is A over 4 pi r times exponential of I omega c over r plus B over 4 pi r times exponential of minus I omega c over r. What is my condition was that for zero frequency, I should get this, right? So for zero frequency, I should have 1 over r. So zero frequency exponential goes to 1. So I have A plus B over 4 pi r. But sorry, zero frequency. This should be equal to, according to our condition, should be equal to 4 pi r. That implies that A plus B, which is arbitrary at this stage, right, should be equal to 1. Right, so we have one condition, so we can at least get one coefficient out. Right, that's good. So we have, so we'll stick to this and say that we have to satisfy that condition. So I have got G of r omega, so I can get this. And now let's substitute this in here. And if I can do that integral, I have a complete solution. That was the Fourier transform. This is the frequency dependent Green's function. Put it back in that, do the integral. I get back my solution G of RT. So if you do that, this is equal to G of R T is equal to, put it in there. So this is A R is not frequency dependent, right? This can come out. So this is A over 4 pi r times exponential omega over the 2 pi times exponential of minus I omega t, and then there is plus exponential I omega over c r. Let me write that in a particular, let me write that next. Plus e over 4 pi r e raised to plus I, no, it's still minus I omega t, but the r's change. Done all this. Won't need this.
Yeah, should not there be like E, right? In the power.
Oh, yeah. Yeah, good, thank you. And this is minus I omega C over R. Good. That's the same as just simple stylistic form of writing. I'm almost going to write it again. But hopefully the integral becomes easier to see. I'm integrating omega, so collect omega in itself, so it's omega times t minus I has been taken care of, so it's R over C. Right, whatever that is, that's not frequency dependent, so the frequency is just I omega plus T over 2 pi 4 pi R times a similar integral, except the sign has changed. Plus R over C. What is that integral equal to? Right?
Which one?
The last integral, the frequency integral,
Delta function.
that's delta function, because that's what Ryan you identified. The time delta function was equal to sum of all the exponentials is always equal to 1. This is nothing but whatever that's constants. So sum of all sine and cosine. Basically, what this says is that if you put in all sine and cosine functions, with all amplitude 1, right? Everything has an amplitude 1. You will get a signal which is basically a delta function. Right? That's a way to generate a delta function. It will just be a pulse of infinitely tiny time. So that's a delta function. So basically, it's solved here. That's what's right here. But that's your G R comma omega, sorry, T, right? That's equal to A times delta function of T minus R over C divided by 4 pi R plus D times delta function of T plus R over C 4 pi R. That's pretty much the solution, but we said at the very end stage, we said we can bring back our origin, right? Wherever R is there, put an R minus R prime, and wherever T is there, put a T minus T prime. So your total Green's function is that is an A, that is the delta of T minus T prime minus of R minus R prime, magnitude of that plus and divided by 4 pi R minus R prime plus B times delta T minus T prime plus 4C divided by 4 pi R prime. Okay. Except this is not very convenient because there are two unknowns, right? A and B. Oh, we have a condition somewhere that A plus B was equal to 1. So we also have this condition that A plus B has to be equal to 1. Right, but even otherwise, we have one unknown. But remember, somewhere in between, Aryan pointed out that what about causality, right? So then we look at both these solutions and see, is this having any causality condition here? Remember T prime. So this delta function means that this is 0, right? Whatever the argument has to be equal to 0. So time is equal here to T prime plus the distance, the time it takes to travel that distance, right? So something happened at R prime. So you have a source, which is R prime, T prime, and your observation is at R, comma T. That's your source time. So you clicked something, and it has to take some time to travel that distance, and you get your new time. That's what is happening here. But here what is happening is t is equal to the observation time is t prime minus the amount of time it takes to travel that distance. This is in the past. So this is past of t prime. Like with respect to t prime, you have to subtract something to get your observation time. That's in the past. This is in the future of t prime. If t is future of t prime, t is past of t prime. At this point, you say that physically, we don't want, we have to respect causality. We don't want any communication which violates causality. So you drop this. So you set this to 0. So choose B to be equal to 0 for causality. VOB. And with that understanding that A plus B has to be equal to 1, you have A equal to 1 then, and then we have our Green's function completely determined. And that's equal to delta function of t minus t prime minus the distance it takes from the source to the observer and 4 pi minus. That's what you want to take home. All those were details, whatever we did just now. We want to have a clear understanding of what this is, and from this point on, we will be using that particular solution. The procedure to get the solution itself is for you to get away from the field for magic. That's not magic, so that's derived. But from that point on, we don't need the details of the derivation. And that's
A lot of steps.
Huh?
A lot of steps.
lot of steps, that's correct. But we need only this, like the essence is only in here. You can forget the whole thing unless I ask you in a homework problem or something, fill in the gap, but I don't think I asked. I don't think there is any homework problem associated with this. I think that is a homework problem where I talk about static case. Some interpretation of this delta function, what this means, what happens if I were to integrate over t, and how that relates to static scenario. But what we are more interested in is how to evaluate this delta function. Notice what is maybe in the last 5 minutes. Yeah, so the challenge in here is about evaluating this delta function. What is delta function? Let's say delta of t minus a, right? T minus s, let's say, of f of t. What is that equal to? F of s, right? So that's the simple idea that this is non-zero only at t equal to s. So that's the value it takes. But this need not be linear, right? Remember, I could have a moving source. Think of an arbitrarily moving source, a charge. So that's a function of time there. Right? A charge is moving, so it's a function of time. Even in the simplest scenario, I will have some function of time showing up here. So let's say this is t cubed, t squared, let's say. With coefficients, I have to get rid of one of the t, right? So that's omega, let's say, times t times f of t. What is that equal to? Or let's make it simpler. What if this was t squared minus s squared? What is that equal to?
T minus s squared, t plus s squared.
F of plus minus
F of
s.
Yeah, the idea is that I think
Yeah, the function.
so. This is zero, right? So T minus S equal to zero. That's when it satisfies it. So here you have to look for T square minus S square is equal to zero. So if T is equal to plus or minus S, there are two solutions possible. So this could be f of S plus f of minus S plus some coefficient. Right? So there has to be some coefficients in there, which we will find out. What if this was T cubed?
Three solutions.
Then there are three, so you have to find the roots of this. That idea is that whatever is the equality there, find the roots of that equation. And the roots are what contribute, and there is something here, which is basically the time derivative of t cubed minus s cubed, whatever that equation is, evaluated at t equal to that root. S or let's say that root, and the same thing in there. So we'll talk about those things. Right, so that's your homework is all about doing this, evaluating this, and that's what makes it hard. For the simple scenario, you can find those roots. In general, you don't know the path of the particle, right? What's the trajectory of the particle, you don't know. If you don't know the trajectory of the particle, or for that matter, even the simple trajectories, you cannot solve them very easily. So that's the challenge.
And if you evaluate the time derivative, T is equal to S.
Yes, so this will be 3t. Oh, that's 0, right?
No, I'm asking you from like the evaluating point T is equal to.
T is equal to root of s,
Oh,
or root of this equation, maybe not s, right? T of r maybe. The root of t, for example, the roots are t is equal to plus or minus s. So in general, there will be 3 roots, and or in general, there could be 10 roots, depending on the equation. And that's the idea. And, and that's called the retarded time. This root is called the retarded time. We will come to it. So that's going to be on Tuesday, and some of your homework, I think 2 of the things probably are about evaluating that function. Okay, I'll start here. Thank you.
Good question.
Yes.
One of the problems in the homework.
Are you attending the talk today?
I can't make it today.
Okay,
uh,
so you want to ask the question now? Okay, ask me. I'll try to.
Just be real quick. I was just wondering how exactly we were supposed to find the eigenvalues for the complex part of it.